Hello everyone, Professor Dustin here, and in this video I'm going to discuss the relationship between simple oscillations and circular motion. First I want to just clarify something which has been happening in the videos and in class, which is using the word simple oscillations versus harmonic motion. So oscillations are generally things that go over and over and over. Yes, they can be springs, but also like complicated systems like waves or planetary motion. All those things are oscillations because there are things that happen over and over with some regularity. Harmonic motion is specifically the case where you have a spring or a system which is very much like a spring undergoing its motion from its two maximum ends in some harmonic way using either sines or cosines. So harmonic motion is more specific. We are really studying harmonic motion. More generally, we're talking about oscillations. So there's a relationship between whatever you call the oscillation stuff and circular motion, which we studied last semester, and so this video is going to discuss that. So specifically, when we talk about harmonic motion, we've been talking about the equation of motion, which is sines or cosines. They have an amplitude, they have a frequency, they sometimes have a phase shift. So that's what I mean by harmonic motion. When I say circular motion, I'm talking about motion that moves in a circle, so objects that move in circles, or parts of circles are also circular motion, although I'm thinking about this as an entire circle. And also specifically, I'm talking about objects that move in circular motion with a constant speed, a given radius. And if you remember from last semester, the acceleration in circular motion is called centripetal acceleration. It's constant and it's v squared over r. So what I want to do is show how all of these things are all related to each other and they're all just different manifestations of the same kinds of motion. So the first thing I want to do is show how this is related to circular motion. And the way I'm going to do that is I'm going to think about this object right here, which is moving, located right at that location. I'm going to think about describing the position of that object instead of in this circular way, but in a xy coordinate system. So I'm going to draw an xy coordinate system onto this circle, x, y. And I'm going to say, okay, what I'd like to do is understand what the x component of that motion is and what the y component of that motion is. So when I say x component, I'm talking about like for the object right there, this right here is its x component, and this right there is its y component. And I'm writing as a function of t because this thing is like moving in a circle. It's a function of t. I'm also trying to relate it back to here, right? Okay, so this is actually pretty simple because this x component of the object which is going in a circle is just that piece of this triangle. So if I even label the triangle with, I have the radius of the circle right there. If I label the triangle with a theta right there, then I can even just write down these as the various trig functions they are. So x of t is going to be related to the sine because that's the adjacent side to that angle. What's the hypotenuse of that triangle? It's going to be the distance r, the constant distance r that goes from the center of the circle out to the edge. So this is simply going to be r. And then it's going to be cosine, because it's the adjacent side, of theta, where theta is right there. Y is again going to be right there, and that's just that side of that triangle, so it's going to be the same thing but with sine. So this is going to be r sine of that theta. Cool, so that's a good step in the right direction because it's starting to look a little bit like this thing, but obviously we're not there yet. This has a t, this is a theta, whatever. So next thing to notice is that this theta is increasing with time. So as this thing goes around in a circle, theta increases with time. So somehow we can change this theta into something which is a function of time because as time gets bigger, theta gets bigger. Now, fortunately, that's pretty simple. So remember that theta is the angular displacement. So just like when you have linear displacements, the amount of linear displacement you get over a certain time is the velocity of the object times that speed times the time, right? So v times t is the linear displacement of that object. Well, we just have to do the same thing here. This is the angular displacement. So the angular displacement is the angular speed times the time. Angular speed, of course, is omega. The time is, of course, t. So in place of this theta, I'm just going to write omega times t. And you can see as soon as I do that, I am right in this situation already. So I'm just going to erase that. So now we have that the x and y position of this object on the circle, moving in a circle, has two components to it, which has x and y component, but they are sort of two copies of harmonic motion. One copy in the x direction, which has an amplitude r and a angular speed omega, cosine omega t, and one in the y direction, which is the amplitude r times the sine of that same omega t. So in circular motion, you have kind of two copies of harmonic motion, where the x direction is just bouncing back and forth like this, just like harmonic motion, and the y direction is bouncing back and forth like this. Okay, good. And notice that phi is 0 here, right? The phase difference is 0. That's just because I picked my coordinate system to be like this, so that when t was 0, I got that the cosine of 0 is 1, just r, and y sine of 0 is 0. So the initial position of the object is right there. So that's why there's no phi. Okay, cool. So that kind of gets us there, but it doesn't really tell us what's going on with the centripetal acceleration. So that's the next thing I would like to do. So the way I'm going to try to tackle that is to write this xy as a vector, a position vector, and then calculate the acceleration from that position vector. Because if I claim that this acceleration is the acceleration of that point, which we know it is because it's in centripetal motion, but if I claim that's the acceleration, I can write down the position vector. I should be able to take two derivatives of it, and I should find the acceleration. So that's what I'm going to try to do. First, that means I'm going to write the position as a function of t, writing r so that I don't get confused about x's and y's. I want to write this as a vector. So the way I'm going to do that is I'm going to write the x position times x hat saying in the x direction, and that x is just that x, plus y of t, in the y direction. So that y hat just means in the y direction. Okay, so now I'm just going to plug in this stuff into there. That's actually not doing anything too tricky. Okay, and you can see I've done that. Nothing complicated, just where I wrote x of t, I plugged that in. Where I wrote y of t, I plugged that in. So I want to get down to the acceleration. Remember that the acceleration is the derivative of the velocity. The velocity is the derivative of the position. So to get from position to velocity, I take one derivative. To get from there to acceleration, I take another derivative. So I'm just going to take two derivatives, one at a time. So the velocity is dr dt. So I'm going to hit this whole thing with the derivative. I guess I'm just going to write that out first. So I'm not really doing anything yet. I'm just writing the derivative that I want to take. Okay, so we're going to take a derivative here. I'm going to take a derivative of this whole function. I have two pieces, one piece here and one piece here, so I take the derivative of them individually. The r here is constant, which is something you have to pay attention to. The r is constant because the circle has a constant radius as it goes around. The thing is moving, but r is not a function of time. So when you take a derivative with respect to time, that just becomes a constant, pulls out of the derivative. You have to take a derivative of the cosine, that becomes a sine. That becomes a negative sign. And then you also have to do a chain rule. So when you take the negative sign here, you have to take the derivative of omega t, pulls out an omega, because that's the chain rule. And then you have to take the derivative of x hat. Now x hat is a constant vector in the x direction. It's a constant vector. It doesn't change in time. So this is also a constant with respect to time, and so dx hat dt is just 0, and so this just gets pulled down with the rest of the function. So let me do that first half first. So we're going to get r times minus sine omega t times omega. That's from the chain rule. And then we just get an x hat because that was one of the constant values, exactly like r, right? We just copied r down. Same thing, just copy x down. Same thing here. That r is constant, just copy it down. Sine becomes cosine now. Now we have a chain rule again. So the derivative of omega t is omega. Derivative of y hat is just y. So this becomes plus r cosine omega t times omega from the chain rule, and then y hat. Cool. So that is the velocity as a function of time. Very nice. We want to take one more derivative to get down to the acceleration. You can see that the pattern is very easy to follow again. So we're going to do acceleration, which is the derivative of the velocity. So I'm going to take the derivative of this. I don't really even feel the need to like write it again because r is constant, minus sine constant, omega constant, right? I'm just taking the derivative of the sine function. Derivative of sine, cosine, derivative of the chain rule of omega t is omega, so I just get an omega squared, so it's quite easy to just read off here. The only thing we have to be a little careful about is that with the sign changes. You got a negative sign when you took this derivative, but you got a positive sign when you took this one. Now when you take this one, you get no positive, you get a positive sign again because the derivative of sine is cosine, but when you take a derivative here, you get a minus sign because cosine, derivative of cosine is sine. So anyway, so I'm going to get an r times now a minus cosine omega t, another omega from the chain rule, so this is omega squared, then times x hat. Over here, we get the r. Now we get a minus sign from the derivative. We get another factor of omega from the chain rule, omega squared times x hat. Sorry, times y hat. Okay, cool. So that is good, but it is a little bit messy. So let's try to clean it up a little bit. We've got an r, omega, and a negative sign in this term, an r, omega, and a negative sign in this term. So let's pull an r, omega, and a negative sign out from the whole thing. So this is going to be minus r omega squared. And then just like, let's write in a big bracket what's left over. We get a cosine omega t x hat plus a sine omega t y hat. Yeah. Okay, cool. Looks good. So that is the acceleration as a function of time. One thing that we should identify right now immediately that's interesting is that look how it relates to the original vector right here. Here, we have basically r cosine omega t x hat plus r sine omega t y hat. We have almost the same thing down here. The piece that's the vector piece, cosine omega t x hat plus sine omega t y hat, that's the exact same as up here. So apparently the vectors are like in the same direction or something. Oh, actually there's a negative sign there, so they're not in exactly the same direction, they're in opposite directions, but they're related to each other, right? And so that's interesting, we should think about that. But let's immediately go on to the problem at hand, which is trying to relate this acceleration to this acceleration, because they should be the same, right? If this is the acceleration of the object, that had better be able to show it from right here. So the way we're going to do that is we're just going to notice that this is a magnitude. This is the acceleration as a magnitude, v squared over r. The acceleration here is not written as a magnitude, it's written as a real vector. But remember, we know how to go from vectors to magnitudes. All you do is you use the Pythagorean theorem. So if I want to find the magnitude of some acceleration, this acceleration in particular, what I want to do is take the square root of the acceleration in the x direction squared plus the acceleration in the y direction squared. Right, so that's what I want to do with this vector. So this is going to be a little bit of algebra, but it won't be too bad. It's going to be the square root of this piece with that in front, so the entire x component is r omega squared cosine omega t, and the y component is minus r omega t omega squared times sine omega t. So the whole thing is going to be minus r omega squared times cosine omega t. That's the x component, all under the square root, minus r omega squared times sine, all squared. Okay, let's take those squares one line down. So I'm going to square everything in here and square everything in here. So that's going to be r squared omega to the fourth cosine squared. Positive sign there because the negative sign cancels, so it gets squared, becomes positive 1. R squared omega to the fourth cosine squared omega t. Plus, again, squared, r squared, omega to the fourth, sine squared. R squared, omega to the fourth, sine squared, omega t. Okay, so now we want to try to simplify this down further. We have to remember our trig functions. And actually, maybe before we remember our trig functions, let's identify some things that are similar. Actually, this, r squared omega squared, and this are the same. So we can pull that out underneath this expression. So I'm going to pull out the r squared omega to the fourth, times cosine squared omega t, plus sine squared omega t. Okay, now we have to remember our trig function identities. In here we have a cosine squared plus a sine squared. You have to remember that's a 1. So one of the trig identities that you kind of need to have in your back pocket is the fact that when you square sine and you square cosine, you add them together, you get a 1. So this whole thing down here is equal to a 1. So that's great. That whole thing becomes a 1. This whole expression just becomes a square root of r squared omega to the fourth. We can even take that square root, which is great. Before this looked impossible, but now it looks like we can actually do it. This becomes r times omega squared. Okay, not bad. The acceleration is apparently r times omega squared. Now notice, it's not quite right yet. It's not quite looking like this, but man, it really looks close, right? We now have the acceleration as r omega squared. We expected v squared over r, but we've got r's, we got velocities. So now we just have to make one additional, remember one additional thing for physics 1, which is just remember that when you have an omega, meaning you have the angular speed of an object, that angular speed is v over r. So that's how you relate the edge speed of an object, this v, to the angular speed. And so actually, if you plug in the v, the omega equals v over r here, you get r. Omega squared is v squared over r. That's a squared, so it's like this, right? V squared over r squared. And now finally, you get the v squared right there, you get the r divided by the r squared, and finally you get the result that we're looking for, which is v squared over r. So this acceleration right here, that is AC. That is the centripetal acceleration. And of course, it has to be. If this is an object which is in circular motion, and we're describing the position of it, the velocity of it, the acceleration of it, we should get that answer, and of course we do. But this is, of course, what physics is about, is finding these relationships and identifying that they are the same. Okay, so I got one more quick thing to do. The overall theme of this video is just connecting these two ideas. And notice they're connected in two different ways. The circle is two copies of harmonic motion, one in the x direction, one in the y direction. But in addition to that, circular motion, which has this centripetal acceleration v squared over r, that is also the acceleration of the object when you think about the two harmonic motions. When you have the two x and y harmonic motions, the acceleration of that two-dimensional object is exactly this. So that's the two main points. Okay, the very last thing I want to do is, because we've got these nice vectors here, I just want to real quickly put the vectors on the picture in the right places to show that they make sense, right? So I've blown up the picture a little bit, so we're just looking at like a quarter of the circle. First thing is just to identify what this vector is. And I'm going to put the position that we care about, which is right there. So that's the position of this object. Let's do the radius vector in pink. So the radius vector starts at the origin, and it goes out to the position of the object. So actually, we kind of already know what that is because we used this vector to find the x and y components, but it's right here, right? So that's r. Because we use the fact that, and let's get the angle in there. The angle now is omega t, right? We use the fact that this was the x component to find that, and that was the y component to find that, so no problem. So really, let's get down to putting in the velocity. And let's do that guy in green. So the velocity is going to be starting from the object, because which thing has the velocity? It's the actual object. So I'm going to start here. But notice the x is negative and the y is positive. So whatever the velocity vector is, it's going to be going in the negative x direction, positive y direction. So it's like going to be going this way. And in fact, it's pretty clear what the answer is going to be. It has to be going this way relative to the object. Because, of course, that's the direction of motion of this circular motion thing, right? So just by taking a derivative, we somehow converted this vector to that vector in the right way so that we get the vector in the right direction for the velocity. That's physics, right? Okay, cool. Let's try to put the angles in a little bit. R omega is just going to be like the size of that vector. The angle is going to be given by minus sine omega t and plus cosine omega t. By a little bit of inspection, it should be pretty clear what omegas those are going to be. Like what angles those are going to be. I think it should be right there. So that shouldn't be a line, that should really be like a dotted line. So now x is sine omega t, that's right there, the opposite side, so that's Vx. Vy is cosine omega t, which is right there, yeah, that makes sense. Okay, so that was the tricky one. Now we're going to go down and do the acceleration, but remember what we said before, the acceleration, this part, the directional part, is the same as the x, right? The same as the original position. So apparently the acceleration has the same directionality as the position, but is just in the negative direction. So we can do that very, very easily. I'll do that in blue. So here's the position vector. The acceleration is in the same direction as the position, but in the opposite direction. Sorry, same, oriented the same way, but pointed the opposite direction. So it's clearly right there. And of course, we knew that too, because the acceleration should be in the negative towards the center of the circle, the negative r direction, which is what we studied when we did circular motion last semester. So I think it's super cool that we just started with the position vector, took two derivatives, figured out exactly what the velocity vector is and what direction it's going in. We basically know everything we could possibly want to know about the velocity. Same with the acceleration. One more derivative got us the acceleration vector. We can confirm the direction of the acceleration vector, which is something which was confusing last semester. We can confirm it now. And also we know the size is r omega squared, which you can also write as v squared over r, the same as we did for cylindrical motion last semester. Okay, great. Thanks very much. I hope this has been helpful in seeing these relationships between the sort of harmonic motion stuff we're studying this semester and the circular motion stuff we studied last semester. Thanks for watching, and I will see you in class.